Hello everyone, I'm excited to present our paper titled ShiftingGolf, Gross Motor Skill Correction Using Redirection in VR. In sports, it's common for athletes to develop bad habits over time, and these can be difficult to correct once they become ingrained. For example, in running there's the issue of heel striking, where the runner lands on the heel first. In swimming, crossover occurs when the hand crosses the center line, slowing the stroke and putting undue pressure on the shoulder. And in tennis, a late forehand is when the swing is initiated too late. Focusing on golf specifically, many beginners and intermediate players struggle to control the trajectory of their swing. A common problem is the outside-in swing path, which often results in a slice that sends the ball to the right. Traditionally, coaching is the most common method for correcting an outside-in swing. However, relying on personal coaching can be time-consuming, expensive, or simply inaccessible. Another existing practice approach involves placing a second ball behind the primary ball. The player initially aims at the rear ball, but actually strikes the front ball. While this drill can help to some extent, its overall effectiveness is quite limited. On the other hand, studies in motor learning suggest that slow, subtle visual motor cues can lead to more effective skill acquisition. By integrating this insight with VR-based redirection techniques, we see a promising opportunity to guide golfers toward correcting their swing habits in a more engaging and efficient way. Next, let's look at some previous research on golf swing training. One example is Virtual Golf Shadow, which supports beginner golfers by overlaying an expert's swing posture with the user's real-time movement, helping them visually identify differences and make posture corrections on their own. Another system, Virtual Club Shadow, displays the club's trajectory on the ground in real time, using color cues to help users better understand and adjust their swing path. In VR, the technique of using visual dominance to induce tactile illusions in users is known as redirection. Asmandian's group mapped multiple virtual objects onto a single physical object to enhance immersion. Ogawa's work found that detecting the threshold of hand movements showed how closely a virtual object must resemble a real one to maximize visual dominance. Finally, Kasuga's group demonstrated that gradual changes in motion targets lead to more sustained learning. These findings inspired our design of different ball movement modes in VR. In this study, we propose a method for correcting a golfer's swing path using VR and redirection. By slowly shifting the virtual ball forward during a VR training session, as shown in the figure, we can subtly encourage players to adjust their swing posture and trajectory. We proposed 3 ball movement modes. The first is a mode, where the ball teleports forward abruptly. Next is G mode, where the ball shifts forward so slowly that it's nearly imperceptible to the user. Finally, I mode alternates between keeping the ball stationary and using the gradual movement from G mode, a strategy designed to reduce any sense of discomfort after training and improve real-world transfer of the learned swing. In our implementation, we use a virtual club model proportionate to a real golf club. The physical club is equipped with optical markers tracked in real time by 12 high-speed cameras, capturing its position and rotation. These tracking data are then mapped onto the virtual club, allowing the user to train within the virtual environment. In our training scenario, the user aims at a virtual flag and must keep their eyes on the ball throughout the swing. As soon as the club head reaches the top of the backswing and just before the downswing begins, the ball subtly moves forward. Here, we have demo animations of the different modes. In a mode, the ball suddenly teleports forward, which is clearly visible in the game view. In contrast, G mode moves the ball so gradually that it's hard to perceive, although you can observe its constant forward motion by watching the ball and floor in the game view. We conducted our end-user study with 12 participants, 9 had some familiarity with golf as beginners, and 3 had no golf experience at all. Each participant tried the 3 modes in a random order. Before training, they performed 12 swings in the normal mode to establish a baseline. Then, after each 36 swing training session with a specific mode, they performed another 12 normal swings to check whether the short-term training effects persisted. For our quantitative evaluation, we measured the club head's velocity at the moment it made contact with the ball. We introduced a metric called velocity bias, which is the ratio of the x component to the z component of the velocity, showing how much the swing path deviates from the z-axis. We also visualized and quantified the difference between the downswing path and the intended swing plane. Additionally, we administered a questionnaire to capture each participant's subjective experience with each mode. On a 5-point scale, they rated whether they noticed the ball's movement, experienced any discomfort from that movement, or perceived a change in their downswing trajectory. This graph shows the velocity bias results. The horizontal axis represents the number of swings, with the first 36 taking place during training and the following 12 after training. The vertical axis indicates the average velocity bias, where values below 0 suggest an outside-in swing and values above 0 suggest an inside-out swing. The farther the value is from 0, the more pronounced the deviation. We see that all three modes demonstrate a clear reduction in the outside-in problem, as the velocity bias shifts from below 0 to above 0 during training. We evaluated the average velocity bias and reveals that after training with a mode, the effect diminishes, causing the velocity bias to drop below 0 once more. In contrast, both G mode and I mode maintain their training effects in the short term. Notably, I mode remains near 0 both before and after training, suggesting a more stable and lasting correction. This slide presents a visualization of the average downswing path relative to the swing plane. Any path to the right of the swing plane is considered outside in, while paths to the left are inside out. Under a mode, the outside-in tendency is noticeably corrected to an inside-out path during training, but reverts back to outside-in after training. G mode also shifts the swing from outside-in to inside-out, and retains this improvement once training concludes. I mode alternates between a gradual shift, similar to G mode, and no movement, leading to strong improvement during the G phase and moderate improvement during the no movement phase. After training, the swing path under I mode ends up closest to the ideal swing plane. Next, we calculate the average distance before and after training and define a learning rate to assess how much each mode improves a user's swing. Values closer to 1 indicate stronger improvement. Our results show that I mode achieves the highest learning rate among the three modes. In our questionnaire, G mode and I mode received predominantly positive feedback from more than half the participants, whereas a mode was rated relatively lower. Most participants clearly perceived the ball's sudden movement in a mode, whereas they barely noticed the ball shifting in G mode or I mode, or only sensed it vaguely. The abrupt teleportation in a mode sometimes disrupted the swing, but G mode and I mode were considered manageable. From the quantitative results, all three modes improved the swing path during training. In particular, G mode and I mode retained these improvements for a short period after training, with I mode positioning participants' swings closer to the ideal plane than G mode. However, the questionnaire results showed that a mode received relatively poor user feedback and was perceived as challenging to execute because of the sudden teleportation of the ball. In contrast, G mode and I mode were generally well received for their subtle, more comfortable ball movements. In conclusion, we proposed ShiftingGolf and explored how VR redirection can guide golfers toward a correct swing by subtly shifting the virtual ball. Thank you for your listening.